Here's sample test problem number 4. A tuning fork of frequency 463 Hz is placed near the top of a tube as shown in the figure at left. The water level is lowered so that the length L slowly increases from an initial value of 20 centimeters. Determine the next two values of L that will correspond to resonant modes. In other words, setting up a standing wave. Well, our frequency is given as 463 Hz. And we know that the velocity of sound, unless otherwise stated, is 343 meters per second. So our wavelength is going to equal the velocity of sound divided by the frequency. That's going to be 343 meters per second divided by 463 per second, and that is going to be 0.741 meters. So that is the wavelength that we're dealing with here. Now, if we set up a standing wave with an open and closed end tube, the first point of resonance is going to occur when we have a node at the water level and an antinode at the open end, and that is going to be a quarter wavelength. So our first length is going to be a quarter wavelength, and that would be actually 0.741 divided by 4, which is 0.185 meters. Or we could say 18.5 centimeters. That would be the first point of resonance. Of course, we're already beyond that when we start, because we're starting at 20 centimeters down. So we missed that point with our water level. So the next point would be a half wavelength further, where we have another node, and this length would be 3/4 wavelengths. So it's really going to be 3/4 times 0.741, and that's equal to 0.556 meters, or we could say 55.6 centimeters down. And our next level at that will be another half wavelength down. So our third length will be actually 5/4 wavelengths, which would be 5/4 times 0.741. And that's equal to 0.926 meters, or 92.6 centimeters. So we start at 20 centimeters, which is just below this first point, 20 centimeters down, and hence our next two points of resonance will be the standing waves at 55.6 centimeters and one at 92.6 meters. So that would be our next two values of L that correspond to resonant modes.